Okay, hopefully that's working now. Thanks. Okay, today we're going to talk about coding style. Whoops, let's see. Okay, so everybody just quiet down. Thanks. So we had one tutorial on this. We're going to go through in this lecture some more tips on writing good readable code. Here's a little snippet of code. What do you think of this? Just if you've, I'm going to clear the queue. Okay, if you got an idea of what you think of this, you like it, you don't like it, you see room for improvement, just press the little button on your table, and you're going to lean in when I activate it and be loud. Okay, so here we go. Okay, G11, you're on the air. I ask everybody else to quiet down because otherwise it's really hard to hear. So G11, what do you think of this code? Where are you, G11? Do you know where you are? I don't know where you are, actually. All right, there's G11. G11, did you push the button on purpose? No? Oh, okay. We're going to go to D11. D11, you're next. I hope you pushed the button on purpose. What do you think of this code? Did you push the button on purpose? Okay, I'm going to clear all of you. I think you guys have never been in this room before. Is that correct? All right. So the little thing on the table in front of you, see there's a little button. Okay, that button will not get you pizza. Okay, you're pushing it right now thinking pizza's going to arrive. It will not arrive. If you push on that button, so A07, just push it right now. Okay. On my screen, it shows up that you pushed it. Okay. And when I go for A07, I'm going to turn on your mic. It turned green, and now you're on the air. Why don't you just say hi to the class? Say it nice and loud. Right into the mic. You got to say it loud. All right. So there you go. So actually, I think I had you muted. Say it one more time. Say it loud again. Louder. Okay, I'm going to turn it up a bit more. One more time. So we're using as our test case. Again, sorry. You in the back, did you hear them? You could? Okay, I'm going to give them a little more volume still, but thank you. Okay, so A07 had the guts to say something to the class. So thank you. Let's give them a round of applause. So. All right, so I'm going to clear the buttons. And from now on, when you push that button, I'm going to call on you. Okay, so don't push it just for fun. It's not a video game. Okay, B12. What do you think of this code? And B12 is right there. Oh, no, I warned you, B12. So now you got to say something about the code. What do you lean into the mic? They don't pick up that well. Say it really loud, though. Okay, so she thinks the code needs indentation. What do you think? Is this code good style or bad style? Yeah, it's terrible. Okay, so this code is like code with no punctuation. If you don't indent your code, your TA will be extremely sad. So this is not going to get you good style marks by itself, but it's like the starting point. This is table stakes. Okay, you got to indent. Also, notice I didn't have any vertical spacing. So we put in vertical spacing, much better. Okay, always do that. Okay, so use white space. Spaces are cheap, blank lines are cheap. Okay, so indent it properly and use blank line to separate functions, to separate blocks of code. Okay, what does this code do? I'm going to give you 40. Okay, so C05, I'm going to call on you if you guys don't quiet down. Going to be awkward, so give it a warning. Okay, so take 40 seconds or so. Think about what this code does. You can discuss it with your table mates, and then buzz in if you think you know what it does. Okay, so I cleared everybody. I'm going to take you in the order you buzz in. You could be a hero if you figure out what this code does. Let's do this again. Huh. Yay. Okay. Yeah, you thought you had 10 minutes. I'm actually, okay, you got 13 seconds left. Sorry. The other time was me messing around with the timer, trying to remember how to do this. Okay. Hopefully you've almost got it. All right. I'm going to give you a little more time. Nobody's buzzed in. Anybody think they know what this is? Okay. Okay, we got C04. So let me clear this timer. C04. And you got to get close to the mic. Speak loudly. What do you think it does? C04. Speak right into the mic. Step 1, find the mic. Step 2, speak into the mic. Okay. I had trouble catching some of that. So can you just say it one more time really loud? Okay. So it's calculating a rectangle area and it's summing them up. Is that right? Okay, that sounds pretty good. So this code is kind of hard to read. I'm not actually going to go to anybody else yet. What I'm going to do is I'm going to go on. And you basically got what this code does. Okay, let me go on to this slide. Okay, I'm going to start my timer again, but it's going to be a short one. And let's see. So let's start the timer and let's show the timer. Read this code. Tell me what it does. Okay, so I'll call on you after when the time's over. So buzz in if you think you got it. Press it. You show up in the queue. Press it. Got quite a few. All right, so G15. You were the first to, you were the first to buzz in. What do you think? Where are you, G15? All right, lean into the mic and say it really loud. Oh, we need our technician again. All right, just say it really loud. It takes the no, we're going to go on to the next person. Okay. A09. Okay, quiet down and say it really loud. Right. Okay. So I agree. So it's doing a definite integral, right? And it's doing it by adding up, finding the average y of this function and basically adding it up. Okay. Why did I show you this? It's to try to demonstrate how important variable and function naming is. These are not really bad names. This is the way early in my career I wrote electromagnetic field solvers. This is the kind of code that I wrote because this is the code that often applied physicists and engineers in that area write. Right? The variable names are not misleading. DI for definite integral, X, A for the D for the step size, Y. The variable names are actually not misleading. They're reasonable. They're what you'd find in a math textbook. but it's still hard to read. And it's not a very complicated function. As soon as I use longer names, it's much easier to understand. So many more groups were able to buzz in and give an answer of what this is. Okay, so use descriptive variable names. You can use underscores to separate things. You can use what's called camel case, where you capitalize every word after the first one. Other naming conventions, when you declare a type, so a class, a struct, start it with a capital letter. Okay, that's a convention that helps people see what's a variable, what's a type. And then variables start with lowercase. So if I declare a class, it starts with an uppercase. If I declare a variable, it starts with lowercase. Much easier to read. Okay, now here's the third version of this code. So you saw this a minute ago. I'm going to basically just go to this slide. Okay, now I've put in proper commenting. Okay, I've got good variable names, even longer function names. Definite integral of 1 over x. I should have a comment above my function saying what it does, so people don't have to read the whole function. So this says exactly what it does. So I take the definite integral of 1 over x from x left to x right. How is the sound back there? Can you hear me, or is it like God mode is too booming? Is it okay or not? All right. So this is what you should do. Comment your function. Every single function in your code should have a comment above it saying what it does. Use very good names. Comment tricky bits of code. In this particular case, for this definite integral, if the integral, the range I'm computing the integral over is not divisible by the step size, I get a little bit of a tricky if statement, so I comment that. Why am I doing this tricky if statement? And I'm using the trapezoidal method, which averages the y values on both sides of the interval. Okay, that might take me a while to figure out if I didn't comment it. So write good comments. Okay, whole function, every function in your code, comment it, comment the tricky bits of code. Okay, so here are 3 different comments that you might have. Now, don't worry about exactly what they're saying. You don't know what programs these are coming from. But you might have this comment at the top of a program for an asteroids game. Here's a comment that I've put above a data structure. So I've defined some structure called student record. I put a comment about what's that structure for, and I've commented what every variable in it is. And here I put a comment above this loop, saying that I'm computing the sum of the array. All right, so take a few seconds and discuss with your table mates which of these comments do you think is most important. Okay, so this is number 1, this is number 2. Let's call them letters, A, B, and C. You know, what's your ordering? Is C the most important, then A, then B? Talk to your table mates and come up with an order and then buzz in once you've got an answer. Okay, and I'm not going to give you long. No, actually, I can only do minutes, it seems. Yeah, I can't find a way to do it. All right, so let's go with that. And that. So you can go for C10 if you want. Let's do it. All right, C10, you are on the air. So C10, right there. You played with the button, you got to give an answer, okay? It's the cost of the button. I know it's very tempting. You know, Dr. Tallman and I come in early, and to get it out of our system, we just play with the buttons for 20 minutes, and now we're okay with it. So say it really loud. What do you think? So you think C is most important? then B is next most important, then A. Okay, what's your reasoning? Why do you think that? Okay, so you like that C is easier to understand, B is not that bad, and A is hard. Okay, so let's see A09. So A09, what do you think? You got to say it really loud. That mic's not working well. Okay, so you say it's a tie because they're all serving different purposes. Okay, so a vote for they're all serving different purposes. They're equal. Okay, let's get rid of this one. And okay, C04, it's your chance to speak loudly and clearly. Okay, guys, actually, let's quiet down. This is really hard to hear. Okay, so you're going with the opposite one. You're saying A is the most useful, B is in the middle, and C is the least useful. So that's actually my opinion as well. Okay, it's A is the hardest to understand. I'd agree, it's covering the most territory, but it's the most difficult for you to work out. This is generally the most difficult for you to work out without some extra information. What is this file for? What's the overall structure? That could take a long time to figure out. If you don't have a comment, you might never figure it out. Commenting data structures is also very important. If you don't understand how the data works in a program, you can't really make progress. This isn't a bad comment, but you can kind of figure it out pretty quickly from the code. So it's not as important. So generally, people don't put enough big picture comments in their code. Try to get those in there. And this is what I just said. So your documentation should be in your comments. Give the big picture, hardest person for someone else to understand. So top of your files, it's a good place for a comment. Class and data structure definitions. If you're making a new type, you're defining a data structure, that's important to comment. Starts of functions. So what does this function do? And then last, tricky code. So big picture is the most important. And the comments that translate C++ to English are not very useful. Okay, so as they get really detailed, and they just tell you this is a for loop, you don't really need them. Yeah, do you have a question? You have to say it really loud though, okay? Let's see if I can turn on your mic. So let's clear all of these, and you are A09. Okay, your mic's on in theory. So I don't know if I understood the comment. So do we want you to comment real code? Comment real code or just comment high level values? Oh, header files. Oh, okay, yeah. So you should have comments in your header files. Okay, all right, so please quiet down a bit. I know it's exciting to be back in person, but it's really hard to lecture over top of you, okay? Okay, so the question is, should you comment header files or CPP files? You should comment both. Header files are extra important to comment. You comment in a header file, why would you use this function? What does it do? In the CPP file, you comment how it works. So yeah, if you're commenting a function and why would you call it, what's its purpose, the best place to comment that is in the header file, because then a person trying to call it can see it right away. Okay, what do you think of this code? So look at this code quickly. Okay, I'm getting really used to this timer. I'm going to turn it on again. All right, and let's see. I'll give you a little while. Talk with your table mates and tell me what you think of this code. So anything you like about it, anything you don't like about it. Okay, B07. You guys right there? You're on the air. Your mic went green. It means you're on the air. Okay, so there's no comment, no vertical spacing. Is that right? So two things against it. Whoops. Okay, let's see. Let's go to C09. So C09, you're on the air. What do you think? So you think comments would make it better? Okay, so few whoops, sorry about that. I might have to turn down the volume a little. Let's try turning one of these down. Turn me down. Any other thoughts? Let's see if we can go to somebody we haven't heard from before. So G07, where are you here? Yeah, where's G07? There we go. I don't know if I can go there. Okay, maybe I have to do this. That's what it is. Forget it. Okay, C10, we couldn't figure out how to go to G7. So C10, you're on the air. What do you think? Okay, so the indentation's okay. It's lacking comments. You don't know what it's for. There's one other thing about this code that is for sure going to lose you marks if you write this kind of code. There's something in this code that's very, like beyond the lack of comments, that's quite bad for maintainability. So we'll take one more shot at this. I'm going to go to E03. Okay, so E03, what do you think? So you have to say it really loud and get close to the mic. Okay, so I think you're saying you don't know what these numbers are, right? Yeah, okay. So I had some trouble hearing you, but I think you're saying you don't really know what's going on. Lack of comments, special numbers. So aside from the lack of comments, which is really bad, I totally agree. Another thing that's really bad is we're using magic numbers. Where does this 20 come from? So we have a size of an array that's just 20 numbers. And notice it shows up in two places. If I ever decide I need a bigger array, I got to change it twice. That's problematic. Another magic number is I return -1 here, 0 here, and 1 here. Okay, so what are those for? No comments. So I could put comments in. That'd be a bit better. But better still would be to return named constants. Okay, so I can say I've got a constant integer called numWeights. Set that equal to 20. I use that for my array. I use that for my loop. Now, if I ever change how big these are, I change it in one spot. Much easier to read, much easier to change. I can define also some other constants in a couple different ways. So this is called a preprocessor constant. It's one way to make a constant in C++. Here's another way. I declare what's called an enumerated type. Okay, so if you guys can quiet down, I would appreciate it, okay? So an enumerated constant is just an integer, and we basically we basically give names to some of these integers because we want to use them as special values in our code. So here I've said there's an enumerated constant that I'm going to call weight return. And I'm defining has neg to be -1, has 0 to be 0, and all pos to be 1. And now I can use those names instead of using these magic numbers of 1, -1, and 0. And now the meaning of the code becomes clear, right? I can return has negative if any values are less than 0, has 0 if anything is 0, and all positive if that isn't the case. That's actually better than a comment. So I should still comment the function, but this is better because these symbolic names make my logic clear. Okay? All three of the ways that I've shown up here, I've shown you 3 different ways to make constants. They're all okay. They're all far better than using these magic numbers. Okay, lots of short functions. So you want to write short functions. They're easier to reuse. You fix bugs in one place instead of many if you have functions that got reused. They make your code easier to understand because they add a layer of abstraction to your code. So they're beneficial in a bunch of ways. We talked about this in the tutorial. Functions should be longer than you think. So ideally, most of your functions are 10 lines long or fewer. Google says you should have very few functions that are more than 40 lines long. So if you look at your project and you see functions longer than that, try to break them up into helper functions. A common one is load map. So a lot of teams are going to lose style marks on load map because it gets really long. Break it up into helper functions. Okay. Okay. What do you see in this code? So give you a few seconds to think about it, talk to your table mates. Tell me there's something in this code that should make you feel not good. What is it? What should we do about it? So let's see. I'm not really going to give you all that time, but maybe it just drives focus. Okay, let's see. Okay, C12, let's go to you. So what do you think about this code? What is it you don't like about it? Right, so we got duplicated code. And whenever you see duplicated code, you should refactor it. So you should rewrite it. It's like changing your essay. So you see basically the same code twice. The only difference is that I'm computing the absolute value, average of the absolute values of this array A, and then I'm computing the absolute value of this array B, or the absolute value average of this array B. So you should not see that. Okay? So you don't want to have this copy and paste coding. It's longer, it's bug prone. So what I should write instead is this. So I make a helper function. So I called it compute absolute average. Maybe I could just call it absolute average. It might be a better name still. And it just takes in an array and the number of values in it, and it computes the absolute average. Your code is not much shorter now because I wrote this helper function and I call it twice, but it is better organized. So when you're reading this function, it's very obvious what each line does here. The action of naming what that function does creates abstraction in your code, makes it easier to understand. And your code is likely to not grow as quickly. As you have more helper functions, you can get more done without adding so much code. Okay? Another rule is don't try to do too much in a statement. So we talked about this in the tutorial. Some temporary variables are helpful. Too many can be harmful. Here's an example where we don't have enough temporary variables. Okay, so we can say, I'm trying to find the name of an intersection, and I want the intersection that came from a certain, this is actually very hard to read. I want to basically get a street segment that comes out of a certain intersection called start intersection. I want to get the to intersection of that street segment, and then I want to get its name. Okay, so that's what this code does. But it's hard to read. I'm doing so much on one line, I have to start in the middle of this group of functions and kind of read my way out. And that's not really natural for a human. These lines are more clear. I've basically broken it down into a few steps. So get a first segment, get the destination intersection, and then get the name of that intersection. So this is a case where breaking a long statement up into pieces is going to help me. All right, so I'm going to pause for a second. So those talking, I'd really appreciate it if you stop talking. Because it is hard to, I'm going to get really tired this semester talking over you all semester. So D05, can you guys stop talking? Thanks. Okay, so the next thing you want to do is group related data into classes. So in milestone 1, you've got global variables. You have to have some. So you might be tempted to do things like this. I've got a vector of integers called from intersection of segment, another vector of intersections called to intersection of segment, and so on. I got a vector of floats, a vector of doubles. So I've got a bunch of variables, and all of these things. So we could have given you an API where we said you can ask questions about a street segment, and you can get each one of these things back. But it would be nicer to group them, because all these are properties of a street segment, so that's what we did. We basically made a data structure called info street segment. Here I call it segment data. And we actually grouped some of these related data items. You can do the same thing when you're creating your global variables. Okay, so here I've made a vector of segment data, and every entry in this gives me all 4 of these things. So it still gives me the same information, but it's kind of organized it. Right? You will access this with a segment ID, and I will give you all this information. And that's just less name pollution. You've grouped your information better. Again, you want to comment your data structures. If you're making data structures, it's a good opportunity to say what they are. So the speed limit, I'm saying it's in meters per second, because that might be vague otherwise. Travel time, I'm saying that's in seconds. So these declarations of data structures are a good place to comment them. When you have something like this, okay, so I just made a vector of segment info, it's a good opportunity to comment, how are you going to access this? What is in this vector? So I often use this notation. I'm going to go from 0 to the number of street segments minus 1. So I'll show you basically how you access this. You access it with a street segment ID. So that can be a succinct way to explain how big is this vector, how do you get at it. So in your global variables for milestone 1, you will get better style marks if you group them into a data structure instead of just having 20 different global variables. And if you group them in the data structure, it's a good opportunity to then put comments on every member of that data structure so you fully explain it. Okay, so I'm going to give you, let's see, I'll give you a minute or perhaps slightly less again to try to find the bug in this code. So discuss it with your table mates. There is a bug in this code. Tell me what it is. Let's see. Do you know what it is? Do you know what the bug is?
I know it is like if you come back to if you have 0, it will get the.
It's not quite it. So I'll come back to you in a minute. Okay, stop that. Okay, E14. We're going to you because I don't think we've heard from you before. What do you think the bug is? Yeah, so you've got very good eyes. Okay, so well done. This is actually a bug that usually people have a lot of trouble spotting because so this is legal C++ code, but it's kind of bizarre. It's a common error. Basically, instead of checking if weights of I is equal to 0, we're actually setting weights of I to be 0. Okay, we meant to say equals equals. That's what we thought, but it's not what we wrote. So this code is broken. If you run this program, for example, with this input, you can see that it should say, it should return has a 0 or has neg, but it says all positive. It doesn't make sense, and it's because of this line. Okay, if you run this, if you compile that program and you tell the compiler that you want lots of warnings. So warnings in a compiler are basically, the code is legal, the compiler knows what you mean, it can turn it into machine code, but it looks funny, okay? It looks like there's something funny about this code you might want to think about, is this really what you mean? So we turn lots of warnings on in your makefile, and that's a good software development practice. You tell the compiler, tell me about funny looking code. So if you compile the code I just showed you, it'll say in this function, check weights, this warning suggests parentheses around assignment used as truth value. So it's saying this is weird. That's actually not a comparison, that's actually an assignment. So you probably didn't mean to do that. So you should not have warnings in your code. And we will take style marks off if you have warnings in your code. The submission infrastructure actually counts the warnings in your code and summarizes it for your TA. Okay, your TA actually looks at your code, but they even get handy summaries from the submission system. Why will we take marks off? Because it's a bad habit. Warnings flag potential problems in your code. Now you could look at a warning and you could say, oh, I checked it out and it's okay. I know this one doesn't matter, and that's often the case. But the problem is if you leave some warnings in, pretty soon your team's project has hundreds of warnings and nobody, or tens at least, maybe hundreds of warnings, and nobody can pay any attention to them. They don't notice when you go from 100 warnings to 101, but that 101th warning could be telling you about something that's a real bug and wasting a lot of your time. So the best practice is to actually not allow any warnings in your code. So we turn them all on, and you'll get a lower style mark if you leave them on. In lots of projects, some of the open source projects I'm involved in, we actually turn warnings into errors, meaning that we actually tell the compiler, do not complete if there's a warning, and that's to force the developer to go fix it right away. So we didn't do that for you guys, but you should still fix them. Okay, a slightly more advanced technique is called defensive coding. So in your code, you can basically write extra statements to make sure your code crashes and tells you if something weird happens. So here's a function, takes a pointer, and I put a comment in saying, don't ever call me with a null pointer, because I'm going to use this pointer and I'm going to dereference it and check if it's equal to 1. Instead of just commenting this, I can actually test for it whenever the program is run. And I can do that by including something called assert.h. And I can basically say, assert that the pointer isn't null. So somebody reading this knows the pointer shouldn't be null, but this also says, if the pointer ever was null and you hit this line, kill the program and tell the person an error message. So it's a stronger check. Okay, so it's better than a comment. This is the kind of error message you would get from it. So you get an assert failed on this line of this file and what the assertion was. So you might wonder, well, what if I need a little bit of extra speed? You know, this is a little bit of extra code. It will slow your program down just a little bit. Usually that's not a concern, but if it was in some key inner loop, you might care. Uh, if you define this variable at the top of your file, you turn off assertions. So this is sometimes when people are making the final release build that they're going to submit in this course or that they're releasing to end users, they can turn off this extra checking very easily. You just define this and it changes how assert works. Assert now doesn't do anything. That's probably a good idea if you use asserts in this course, because once you submit the program, we test it, and if it crashes, you lose marks. So you might say, you know what, if it's got any hope of completing, I'd rather it completes. So I'll have assertions in when I'm running it, but when I submit, I'll turn this on so that the final testing doesn't have these extra checks. Other good practices, if you delete a pointer, so you got rid of something the pointer's pointing at, if you set it to null immediately, now if you try to use that pointer, like here I tried to dereference that pointer, you'll crash right away. It's guaranteed. Basically, there's some really important data that the operating system keeps at address 0. So if you ever try to access the data at address 0, which is what I'm trying to do here, the operating system will kill you for sure, and you'll get a seg fault. If you didn't set this pointer to null, then this code is not legal, but it might crash and it might not. And if it doesn't crash, it's worse, because you just wrote over some data, you don't know where it is. And the last thing you can do, which is a more advanced technique, but is done a lot in bigger programs, is you can write validity checkers. So some function that you call that just checks, does the program state all make sense? I have all these data structures that interact in various ways. Let's walk through them all and make sure they make sense. If they don't, we can print some error messages, or we could kill the program. Okay. Here's an example I found online of where they should have used validity checkers. So there was a cake printing service. You sent in, filled out a web form. You said what you wanted on your cake. And whoever wrote the program didn't expect basically non-Latin characters. So there's some Aunt Elsa who was going to get a birthday cake, but there were some unusual characters in the message. And instead, she got a bunch of HTML message errors that probably confused her at her birthday. So if they had used some validity checkers, hopefully they could have figured this out before they actually printed all the HTML error messages on the cake. Okay, so the key to maintainable code is to remember that code's read many more times than it's written. So you have to make it readable. And it's read by other people than you. Code is going to be modified a lot. To make it easier to modify, make lots of small functions, avoid repeated code. Keep your tests with the code. So in this course, we're showing you test-driven development by having lots of unit tests that you run all the time. That's the way you want to keep your code working. Have automated tests that are easy to run. Keep your documentation as much as you can in the code. So you might have one very high-level document that just describes the overall architecture of the code, maybe a README file, but the vast majority of your documentation should be in comments in the code so that it stays with the code, it gets updated with the code. Do code reviews. So within your team, read each other's code, give each other feedback. You all become better coders and you see what other people can read and what they can't read. It makes you better. I mentioned this in a tutorial. At Google, which has a lot of best-in-class coding practices, the code you submit to the revision control system is actually not fully committed, not visible to others until it's reviewed by an expert in the system you're working in, who says it fits the philosophy of the system and it is expected to function well, and read by a style expert for that language, who says, yes, this is good use of C++, it's well commented, it's well structured, I like it. Only once it passes those two reviews does it actually make it in and be seen by other people. If you haven't read it yet, go read the Milestone 1 project management and style rubric so that you know what your TA is looking for before you're graded. Okay, so that's it about code style. I got a few minutes, so I was going to tell you a couple things about how this course links to others. So we'll do this a few times during the course. So in the last few lectures, we talked about project management and how teams work. So you learned about that in APS 111 and 112. But the main technique you used there was more waterfall driven. Write specifications, write more detailed design documents, well, a high-level design document, then more detailed, and so on. So what we're teaching you is project management that's more iterative and agile, which is more commonly used in the software industry, but also spreading elsewhere. Where can you keep learning about this? APS 343 is about engineering leadership. So for many of you, for me, some of the most interesting parts of my career were learning how to lead teams. So this course is about that. In your 4th year project, you'll work in a team. So you get more experience on a more open-ended project that's specific to you. And the iLead Institute at U of T runs frequent workshops on leadership. So you can go check out on this link, what are they doing? And go and get some of that experience in project management and leadership. Yes, the other thing we've been talking about is software development. Okay, so in APS 105 and ECE 244, you learned about writing smaller programs. Here you're learning about larger programs, writing code in a team, higher performance. So we care more about performance than those courses did. After this course, where can you go? ECE 344 teaches you how software interfaces to hardware. So how do operating systems work? The really low-level code. ECE 444 teaches you more about how to code in a team, how to complete large projects, how to use Git in different ways, how to collaborate as a team in different ways. And ECE 345 is all about algorithms and data structures. There's no coding right now, but it basically goes through analyzing different data structures, different algorithms to see what'll be fast. And you're going to use all these skills in your PUI and career. Okay, and this is the last slide for today. Often I get questions from students about what programming language should I learn? Should I learn C++? Well, you have to. Okay, we made you learn C++, but was that the right decision? Maybe the profs are crazy. There's no perfect decision to this, be honest. And there are many programming languages, so you'll never be able to learn them all, but you're going to have to learn more than one in your career. Okay, so just give me 90 seconds more. So those talking, just wait for a second. So this is from Spectrum. So the IEEE's magazine. It's their assessment from this year of the relative importance of different programming languages. They base it on job postings, projects, GitHub, all sorts of things. Okay, so Python's number 1. How many people know Python? Okay, so a few. It's actually a good idea to learn. One opportunity to learn it, is this course, ECE 444. It programs in Python. Python is different from C++. It's much slower. It's 100 times slower than C++. But you can write programs in it fairly quickly. So it's good for tying things together. It's good for what's called scripting. But it's harder to write really big programs in it, and your programs don't run as fast. So you want to know both. Then you've got these languages. Okay, so we've got C++, we've got C, we've got Java, and we got C#. These languages are very closely related. So C++ is C with classes added to it, plus a bunch of other more recent features. So C++ includes all of C. C is still used a lot for real-time programming in embedded systems and robots and so on. C++ is used for bigger high-performance systems like game engines and databases and so on. Java's original code name was C++. So Java was created to be a simpler version of C++. It's not quite as fast, but it's a little bit safer, a little bit simpler. And it can also be run, after you compile it once, it will run on any computer. So if you know C++, you actually know a lot about Java, because it actually is a simplified form of C++ and a few changes. Who knows what C# is? Okay, so a bunch of you. So C# is Microsoft's, they did not want to license Java, so they made Java with a new name. Okay, C# is, it doesn't use exactly the same syntax, but it's very close. It was basically created by Microsoft to be a competitor to Java. So 4 of these languages, even though these look like a lot of languages, these four are really closely related. You get good at one of them, you'll be pretty good at the others. And then JavaScript is used a lot in web programming. Also not that high performance, higher performance than Python, lower performance than C++. You can write programs quite quickly because it's very loose with its type system. It's also very easy to introduce bugs. So my recommendation to you is basically of these top 6 languages, you should be pretty good at 4 of them right now. You're good at C and C++, and Java and C# are easy to learn. And then some point in your career, you're going to want to learn one of these kind of more loosely typed, can make it run, can get it working sooner, but run slower and has more potential for bugs languages. So Python or JavaScript or both. Okay, so thanks everybody. That's it for today.
I think one of the mics is on, and so then we're getting feedback from you.
Oh, okay.
Holy stick around.
Yeah.
I have to